I'm ready to go. Hello, my name is Evan Witz. This is Math 219. We are going to be discussing a couple of problem in the chapter Lines and Planes in Space. If you have any more problems that you want us to do, as always, post them on the forums. So the first problem that we're going to be working on is this one. So we are going to find the equation of a plane through this point 9, 2, 2. And this plane has to contain the line x equals 1 plus t, y equals 2 plus 2t, z equals 3 plus 3t. So I'm going to go ahead and step off for a second. If you guys want to try and do the problem yourself, feel free to pause the video at this time. And when I come back, I will go ahead and solve the problem myself. All right. So I went ahead and copied the important information for this problem down over here. So we have a point 9, 2, 2. We have a line x equals 1 plus t, y equals 2 plus 2t, z equals 3 plus 3t. And we want to come up with an equation for a plane containing both this point and all of the points on this line. So immediately, we know one of the vectors that represents the direction vector on our plane. And it would be the direction vector of this line. So 1, 2, 3. So this vector has to be on our plane. So it's orthogonal to the normal vector of this plane, whatever it happens to be. So the next thing we're going to want to do is we're going to want to find another vector that lies on this plane. So we have one point already here, but we don't have another point to construct another vector. So what we're going to want to do is we're going to want to use this line that we have here in order to construct said vector. So if we just go ahead and plug in t equals 0 arbitrarily. Actually, you know what? I'm going to plug in t equals -1 because that just gives a nice little. So if I go ahead and plug in t equals -1, x equals 0, y equals 0, z equals 0. So this is a point on our line, and as we know, this point has to be contained in our plane. So q is equal to 0, 0, 0, which means that our vector pq, so this is, I'll just call this vector v, our vector pq is equal to the difference between, or I'll do qp just because positive numbers. Gotta love those positive numbers. Vector qp is equal to 9 minus 0 is equal to 9. 2 minus 0 is equal to 2. 2 minus 0 is equal to 2. So we have two vectors that lie on our plane. So what we're going to want to do is we're going to want to construct the normal vector from these two vectors. So in order to do that, we take the cross product of these two vectors. So I'm just going to go ahead and write that out here. V, PQ, X, Y, Z. 1, 2, 3, 9, 2, 2. Okay, so that means that the cross product of these two vectors is our normal vector. So if we go ahead and calculate that out, the x coordinate is going to be 2 times 2 minus 3 times 2, which is -2. So -2 in the x direction. The y coordinate is going to be 1 times 2 minus 3 times 9 is equal to, let's see, that's -25. But remember, the y coordinate is negated, so that means it's going to be +25. And lastly, our z coordinate. So go ahead and cover these up. 1 times 2 minus 2 times 9, let's see, that is going to be -16. -16. So there we go. We have the equation of, so we have our normal vector now. So these are going to be the coefficients of our equation of our plane. So this is A, this is B, this is C. And now we just need to choose our x naught, y naught, z naught, which we already have this very lovely point up here. So I'm going to go ahead and say that is equal to our point x naught, y naught, z naught. And now if we go ahead and plug this into the standard equation for a plane with a given normal vector through a given point, this gives us negative 2x plus 25y. Okay, so let me rewrite this really quick. Negative 2x minus 0, which is equal to x, plus 25y minus 0, minus 16 z minus 0 is equal to 0. And you can just eliminate the minus zeros, so negative 2x plus 25y minus 16z is equal to 0. And that is how you find the equation of a plane given a point and a line that the plane needs to contain. So if you go ahead and plug x, y, and z into this equation, you'll find that this identically works out to be 0. So no matter what value your t is, you will always end up getting that a point x, y, z on this line satisfies this equation. And if you plug 9, 2, 2 in, again, the same thing should happen. So ultimately, this ends up working out. So that concludes this practice problem for lines and planes in space. If you have any more suggestions, feel free to post them on the forums. And thank you very much for your time.